Good afternoon and welcome back to the session. We have Professor C.K. Raju with us, who's the author of a very extensive list of publications, of which Cultural Foundations of Mathematics describes what he'll be talking about today, the theft of calculus from India and its subsequent Western misunderstanding. He's a visiting professor of mathematics at IIT Mandi and is currently trying to correct its bad colonial teaching through his course Calculus as Ganit. His paper today is Busting Macaulay, the epistemic test, the theft of calculus by Christian discovery, and the myths and superstitions in the present day teaching and practice of axiomatic maths.
Rather a provocative title, and intendedly so. So let me start with Macaulay, because so much is said about Macaulay, but his claim that he made in his minute on education, that the West is immeasurably superior in mathematics and science, and therefore the best we can do is to copy it. But what I want to say is that this claim was just a mutation of an earlier claim, a fanatical Padres dogma of Christian supremacy, which was, well, maybe you can look at this paper if the internet works. Yes, so Euclid Must Fall, this paper, tells you about this dogma of civilizational supremacy, which was started long back in the 4th century when the Padres got power in the Roman Empire. They seized control over the Roman Empire. Then it had a later day mutation during slavery into a religious dogma of racist supremacy. When the slaves suddenly converted to Christianity, they could no longer keep them enslaved on the grounds that they were non-Christian, and therefore they changed into this dogma of racist supremacy. So this is not just I who am saying this. The Native Americans who were all killed, they have been fighting about it. They have taken up the issue finally. And I have an article also on that, on how that affects the religious roots of white supremacy and how it affects our teaching of mathematics. Although they did not very much like that, but anyway. So Macaulay, incidentally, did not propose education only in India. He proposed free and compulsory education for the British poor. And he did that because he was afraid of revolt by the British poor. Very explicitly says so. And of course, it was 100% church education then, for there was no secular education in Britain in Macaulay's time. First secular law for secular education came in 1870. Why education? Because he said that is the cheapest means of controlling revolts. He says it explicitly in a speech to British Parliament. And you can see this article also of mine on education and counter-revolution. That was his objective. So decolonizing the hard sciences, his original title was different. They changed it. So that's the idea. And so the point I'm making is we should stop blaming Macaulay. Macaulay was a single individual, and the same education system is found everywhere in the world. It's found in the French colonies, it's found in the Dutch colonies, the Spanish colonies, the Portuguese colonies, where Macaulay never went. So it is church education which was globalized in India by Padres, not Macaulay. It was education built by Padres, and so declaring Macaulay as the cause of colonial education shows extreme lack of Shatru Bodh. At least know who your enemy is. So the doctrine of supremacy was supported by false history. This was a systematic thing that was done by the church in the 4th century when it seized power and weaponized Christian dogmas. And so the doctrine of sin, doctrine of eternal damnation, etc., turned into instruments of power. Likewise, false history was also made into an instrument of power. And it was, well, I have some Orosius somewhere. I don't know where Orosius has gone, but let's forget. Orosius in the 5th century was the first person to write his history against the pagans. And then, of course, I have a little booklet on this, and this is whether is science Western in origin. All these chaps are hanging up and upside down. So that is Ptolemy, Copernicus, Euclid, and Newton. So, and there is also a back cover that maybe you can read that this is what happened, and science is claimed by the West, and mathematics is also. So this is all far before, long before Macaulay. All right, so the point is that this was given they translated a whole lot of Arabic texts in Toledo and gave them a theologically correct Greek origin so that they could be used as texts in the universities, and they wanted to grab knowledge to win the Crusades. So they grabbed this knowledge. And later texts were declared of Christian origin on the inquisitional model. So inquisitional model, are you able to read it? I am still having some difficulty in reading it.
Orosian model.
Orosian model. So Orosius was the first chap in the 5th century to write history against the pagans. And his idea was that God punished and rewarded people in this very world, and history proves that, and therefore he wrote history on that way. There was a Byzantine Greek model. There was a crusading model, which I was just talking about. There was an inquisitional model like Copernicus, where you take things, and during the Inquisition they were afraid of accepting that they had a heretical origin. Then there was this model of Christian discovery, and so on. So there were racist model and colonial model after that. So this is part of my paper. Where is the paper? So this is the paper which I just showed you. You can take a look at that and look at all the details on that. So the idea is to deny the heretical origin, and it is, of course, a genocidal religious dogma. And you should understand the meaning of Christian discovery. It does not mean discovery in a simple sense. It's a theological term, and its meaning is elucidated by the judgment of the US Supreme Court that regardless of prior knowledge or regardless of prior occupancy, any piece of land or knowledge belongs to the first Christian to spot it. And therefore, Native Americans lost their right to the land when they were spotted, they were discovered. So this is also what I'm saying about the discovery of calculus by Newton. I'm saying he spotted it and he claimed it exactly the way Columbus claimed America, that he discovered, and exactly as Vasco says he discovered India, regardless of the earlier occupants. And eventually all science was claimed on that basis. So now let me come to the theft of calculus. So I think we have got our fundas clear, what we are talking about, that false history, systematically false history running from the 5th century, running through the Crusades, through the Inquisition and so on, very systematically false history, not one person or somebody doing it, institutionally done across the board. So let's look at calculus. So everybody here, I'm sure, knows about this paper of 1832, it was presented, and 1834, it was published on the Hindu quadrature of the circle. So he's talking about the infinite series in these texts, which are the Yukti Bhasha, the Karan Paddhati, the Sadratnamala, and the, which is the other one? Tantra Sangha, yes. So he's talking about these 4 texts. And now the question is that we have all these. Now there's a later version of it in this book, which was mentioned in this book, and it is about the transmission of calculus. Those days I was being much more polite, and I used the term transmission and not theft, because I think now you have to use correct terms because people get misled. So let's use the word theft where it applies. And so the fact is that
I never knew that you were polite.
I was polite. As you can see, I was using the word transmission, which is a very polite term. So we know that Madhav's earlier infinite science series was claimed by Newton. So this is I suppose all of you are familiar with it. This is just an extract from the book. and all of you must be familiar with it, so that's not a... Pardon me? Calculus chore. Yes, it's much worse than that. You see, it's much worse than that. If it's just story, it's all right, but it is much more than that. Sina Jori is also there. So there was the infinite series for pi, which was claimed by Leibniz, and there was the infinite series for the arctangent, which was claimed by Gregory. So this was the infinite series for the arctangent. And now the issue is, why are these two series the same? And well, what they were used for. They were used for precise trigonometric values, and we know how precise they were. This is very important. They were extremely precise trigonometric values that we are talking about. And this was the motivation really to steal them, because they were extremely important for the basic means of producing wealth for Europeans. So how do we explain the stark similarity between the earlier infinite series and the later infinite series, which are today attributed to Gregory, Newton, and Leibniz? All right, so onus of proof. According to academic norms, if somebody claims, look, I did exactly what that chap did, and so many people have claimed like that. So the onus of proof is on the person who comes later. He has to explain how he did it independently. Nobody has explained. All right, and especially when their character is suspect, they have stolen 3 whole continents. So, calculus is a very minor thing. What is the big deal about stealing calculus or anything else or any piece of science? So they have stolen, they have killed people, everybody there in those continents, and there are just some few people surviving. So the onus of proof is on them. And there is a double coincidence that we are talking about. Not only was it independently of India, but independently of each other. So the Roman Catholics to whom the calculus first went, like Cavalieri, who was Galileo's student, Galileo had access to the Jesuit archives, and Pascal and Fermat and so on. And then the Anglican Gregory, who brought Indian calculus from Padua to the Protestants, Newton and Leibniz, who later claimed credit for this. So you have to explain that double coincidence. Nevertheless, though the onus of proof is on them, nobody has ever proved it. I did give... I want to say that he stole it. Newton stole the calculus, and since theft is a criminal offense, you must have proof beyond reasonable doubt on the standard of criminal law. That is what I proposed long back, 25 years ago, in my Hawaii article talk, and there was this article. So this is the paper on computers, mathematics, education, and the alternative epistemology of the calculus. That alternative epistemology is very important. All right, so we'll come to that. So this was a new standard of proof, and the new standard of proof was just this, that given that there are such wide claims of transmission from Greece and so on, you need proof beyond reasonable doubt. And therefore, I suggested motivation, opportunity, documentary proof. This is from the Hawaii paper, and circumstantial evidence. So actually, you don't need documentary evidence. You don't know thieves who leave by hand notes. Okay, I stole this. No, I just added it for effect. So we do have to consider that what is available. So this is based on the current standard of criminal law, which is quite distinct from the usual standard of proof used in history, which is balance of probabilities, or in civil law. But this standard was, such a high standard of proof was never used in history, and contrary to Wikipedia says there is no evidence, it doesn't provide evidence. I did provide evidence, and well, that is just the habitual lie that you can get from Wikipedia. So the initial proof for the theft of calculus was these four: opportunity, motivation, circumstantial evidence, and documentary evidence. So opportunity is very clear. Vasco fled from Calicut to Kochi, and he founded the first Roman Catholic mission, and they taught the local Syrian Christians whom they wanted to convert. But they not only taught them, they formed a bond with them, and they used them as informants to gather and translate the Indian mathematics texts to get information about them. So there was contact, there was ample opportunity for Europeans to steal these texts, and these texts were being mass translated into Latin by Jesuits on the Toledo model of mass translation of Arabic texts. So the motivation, why did they want these texts? So they were doing something, they were translating a variety of texts and so on, but why did they want these math and astronomy texts? Because of navigation. Navigation was a critical issue. There was a European navigational problem. I'm not saying that navigation was a global issue. I'm saying there was a European navigational problem. They did not know how to navigate. So there are three problems of loxodromes: latitude and longitude. solution of all these problems required accurate trigonometric values, and you saw those were the most accurate trigonometric values then available. So determining latitude in day also requires that you are measuring by measuring solar altitude at noon, you also need to know the declination. And to determine the declination, you need to have a good, I'm not showing you all the slides because that's just a textbook, 9th standard textbook. I'm sure everybody understands these things. So you need an accurate date of equinox or an accurate calendar, which was missing. So the Gregorian reform of 1582 was done for that purpose, because the Christian calendar, it's not the Julian calendar. If anybody tells you that, it is false. You can't confuse Vikram Samvat and Shak Samvat. No? Where does the Christian calendar begin from? It begins from something which is called date of AD BC era. So it has nothing to do with Julius Caesar. That was, Julius Caesar was long before that. So this is different, it's an officially adopted Christian calendar in the First Council of Nicaea. So the Mercator map, we know the Mercator chart, it is just the usual map of the world. So there's nothing new. The important thing is, why is this Greenland so big and Africa is so small? Because it bloats areas at high latitudes, because here the formulae are that we are integrating sec of x, and therefore the area at top will get bloated, near the poles will get bloated by a large amount, by sec square phi to be precise. Then latitude, as we know, Columbus did not know even how to determine latitude. He recorded when he was near Cathay, 41 degrees, when he was off Cuba, 20 degrees. So he did not know how to measure latitude. Neither did Vasco. He was equally ignorant, and he had to hire a navigator to come from Malindi to, he was creeping along the coast all along, and then from here he went across the sea. He could not go across the sea without a chart. He went with the help of Indian navigator, because the trade in the Indian Ocean was established a long time in the past. So he called the person whom he hired Mualim Kanak. Mualim means wayfinder. Kanak is just like Ganak, is a calculator. So they used a wooden board with 2 strings. That is the wooden board, and it has knots in harmonic proportion. It's a very sophisticated instrument, and the instrument is held between the teeth. So to measure the angle between the pole star and the horizon, you want to know the angular elevation of the pole star, measuring that. And the pole star is called cow in the Arabic Malayalam language, which is used by the Mapulas. And so Vasco said pilot was telling the distance by his teeth, because teeth is also, the word for teeth is also cow. So he just recorded the mistranslation. Of course, it's not just a mistranslation. There is always in all these mistranslations, whether it's the word sign or whether it's the word surd, there's also a conceptual error. And the conceptual error in this case was he did not understand that it's a harmonic scale, and he did not understand that you can use 2 harmonic scales. So he took back a copy of the Kamal to have it graduated in inches. Can't be done because it's a harmonic scale, like you have the knots are not linear like on a flute. So harmonic proportion. And he did not understand, and no Westerner till today has understood that you can use a 2-scale principle also with harmonic scales. That I did, but nobody has picked it up. So they are just drunk in their supremacist idea, sense of, see, this is what James Prinsep wrote. He was at the Reserve Bank. I certainly imagined that nothing could be more primitive than my Maldive friend's Kamal, when lo, here is something even less advanced in ingenuity. Now, who was lacking ingenuity? Prinsep, who did not understand the construction of the instrument, or all these people who did not understand it for another 200 years? Who lacked ingenuity? So this is how they made these remarks, and this is what happened. And they did not have the common sense to ask, how did Lakshadweep Islanders routinely navigate to small islands without accurate instruments? So they're very small islands. So you need an instrument with accuracy of at least 11 miles. So they did not have that thing. And longitude, of course, we know it's a well-known problem that they could use the elevation of the pole star only in the Indian Ocean, but they could not use it when they went to the southern hemisphere, and they could not use it they could not use any one of the several Indian techniques of determining longitude, like the one you have in Laghu Bhaskariya, where he is solving a plane triangle, plane navigational triangle. I'm sorry, I can't spend too much time on that. So it's just using the Pythagorean proposition, and this required an accurate knowledge of the radius of the Earth, which the West did not have, which Columbus did not have, and which the West did not have until quite late, and therefore they had a longitude problem, and therefore governments were investing so much money in determining longitude. The important thing I want to say is that Brahmagupta said that, bhuvasasya agyanat vyartham deshantaram, right? The ignorance of the Earth's radius makes it futile to calculate deshantar or the longitude. All right. So he said that. So you need to know that. They did not know that. And therefore, anyway, he also said that they using plane triangles is a gross method, as per the disciples of Aryabhat, who would say that because of the curvature of the Earth, you have to use spherical triangles. All right. So you have this in Mahabhaskariya. Now they had a very crude method of heaving the log. You throw a log overboard, tie it with a string. You count the number of knots and see how many knots go out, and it records the number of speed and number of knots in a logbook. That's where the word logbook comes from. And then you are going. This is a notoriously unreliable method of longitude or speed determination, of longitude determination. Therefore, it became a very major problem because so many people died because of bad navigation. So they still needed accurate trigonometric values even to solve the plane sailing triangle, right? So if you have a triangle, if you have two things, so if you know the distance, you know the cos angle, it's a right angle triangle, so you can solve it. But even for that, you need good trigonometric values, which they did not have. Okay, so circumstantial evidence is, of course, the meridian of Greenwich, for example, is a copy of the meridian of Ujjaini or the Yamyotari. This is from the Surya Siddhant, that the meridian crossing from the poles through Ujjaini, Kurukshetra, Rohtak, etc. is the, and Sri Lanka, not Sri Lanka, I'm sorry, Lanka, which is not Sri Lanka. And of course, there's Fermat's challenge problem, which is known as Pell's equation. There is Pascal's triangle for binomial coefficients, which is known as Kandameru or Meru Prastha. This is part of the way the meter that you use, Guru, Laghu, and so on, to recite the Veds. So it is a very old thing. So you have the copy of the binomial coefficients. And there is Aryabhat's recursive method, or Euler equation, Euler method. Now this is copy-paste from my notes, okay. So Neil Kant's planetary model is there, which was called the Tychonic model. It did not just flunk, because it's not that you had a heliocentric model and everything else just fell down. It survived in China. The Jesuits took it to China. And then you have, of course, Madhav's sign values. If you look at Clavier's sign values, which are to the same radius, and they are interpolated versions of that. You have the quadratic interpolation formula due to Brahmagupta and Vateshwar, which is the same thing as Stirling's formula. Maybe you understand it in this form. So it's a quadratic interpolation formula, and this was there from that time. And there's, of course, documentary evidence, which is Matteo Ricci's letter. So he is writing just before the Gregorian calendar reform. He's in Cochin, and he's writing that he's looking for Muiro Honorado, so an honorable Moor or Brahmane intelligence, intelligent Brahmin, to tell him about Chronicos dos Tiempos, methods of chronicling time in India. That he is looking in Cochin, because he was in India before he went to China. But it's impossible for them to admit that they used heretical knowledge to reform their calendar, because it's a religious calendar. And what was corrected was also the date of Easter. That is why the Pope corrected. It wasn't just done by a secular authority. So, of course, it was not the Julian calendar. I've already said that. So they gave some story about some Alphonsine table. It was calendar was known to be defective from the 5th century. Beginning of the 5th century, it was known to be defective. After 1,000 years, they do, and they talk of some Alphonsine tables. If they were there, why was Ritchie searching for this knowledge from India? So I will skip that. Anyway, Wikipedia says I have provided no evidence in my book, so you can go with that. Now let me come to the epistemic test, which is the central thing I want to talk about. So in my 2007 book, I introduced a new thing, which is the epistemic test. And so there's an article on that you can look at. which is on marks and mathematics, the epistemic test. I will not close it. We can come back to it. That people who still don't fully understand the knowledge they do, like students who cheat in an examination, they understand something, which question to copy. But beyond that, they have a problem. They understand something, and they may understand more or less, but usually they don't understand. And that is what I developed while teaching. When you find students who are sitting next to each other, turning in identical answer sheets, then you call them and question them, look, what have you written? Do you understand what you have written? And most of them could not answer. The person who cannot answer had obviously not written it. So lack of understanding is proof of copying. That's the point. All right, and then because if Newton's fluxions and Dedekind's axiomatic real numbers do not incorporate a correct understanding of calculus, how do you know it is the correct understanding? Then today calculus has to be taught differently, which is what I'm doing in IIT Mandi, and that is my course. This is online. If it comes online, it's taking a lot of time. This connection is slow. Okay, I'll come back to that. It's not giving a 404 error. Let me come back to it after some time. So, it is just, is it there? Has it come up? No, it's not coming up. I think my phone is inadequate for that. So, I want to give some example of this Mandi course is called Calculus as Ganit. So I'm saying that there is a different way to teach calculus, which is a better way to teach, which does not incorporate the lack of understanding that the West had of calculus. It still has, because it's still taught that way. So you have to at least compare. Where do you find the comparison done? Nowhere. So let's take the epistemic test in the case of arithmetic. We know that Greek and Sanskrit and so on are very similar. I won't bother to give you details. They are all language scholars here. So what I want to say is that there are no large numbers in Greek and Latin. The largest number they knew was a myriad, and in the English language it connotes countless. So I have a lot of literary quotations from that. I won't go into that, from Mark Twain and so on, from Ezra Pound. So a whole lot of literary quotations that myriad means an uncountably large number. You want to see them?
Some myriads of quotations.
Yeah, myriads of quotation. Okay. All right. So Sanskrit numbers go on. So right from the Yajurveda, you have a number which is very large, which is the Parad, which is 10 raised to 12. And in the, you have Tallakshan and Parmanuraja Praveshanugata. In the Lalit Vistar Sutta, which is the life of Buddha, chapter 12, and you can, he was asked to name numbers after 100 crores as a condition for before his marriage. So Shatakoti, so he goes on, and these are all the names that he gives. And well, it's a long list. This is only up to Tallakshan. From Tallakshan also it goes on. So you can find it somewhere in my writings. But the Greeks and Romans would have clunked because they didn't have names. Like everyday journalists today, they will say, after 100 crores, what is it? 1,000 crores, and what is it? Lakh crores, and what is it? 10 lakh crores. They don't have names. All right, they don't have names. So we have got de-education. You got de-educated because of this sort of thing we have learned. And essentially I am saying that Greeks learned their number names from Persia after the Persian conquest, and the Indians and Persian number names were anyway similar. So there is this Dara Vas. Oh God, this graphics it won't get. Very slow. Even the first one has not come. So anyway, Dara Vas shows Persian tax collector. I would like to show it. That's why it is here. Maybe I should have taken your internet connection. So it shows a tax collector scene where the Persian conqueror is using an abacus. And this vase is in Italy. It is dated to minus 3rd century, minus 4th century. And it shows that Greeks had to pay taxes, and so they had to learn the Persian system of arithmetic to pay them taxes. It's an Achaemenid conquest. It's a real conquest, unlike your Aryan race conquest, which is mere myth. And in the Persian, you do not have, you have Bevan, and this, my source of information is Zoroastrian, where it is available in Gujarati script and so on. So they had the same small numbers, but no large numbers. And this was because they had primitive pebble arithmetic, And we know that Indian arithmetic went to Baghdad. From Baghdad, it went to Europe. And one of the first persons to take it up was Gerbert, who made epices. So he made, this was the thing he did. So these are the first Arabic numerals when they went around 976. And basically it's the same, it is pebble arithmetic, pebbles on a board, except that the number is written at the back of the pebble. That is the epices. Then Fibonacci. Fibonacci got it next because Gerbert didn't understand the very fact that he made a foolish mistake of constructing an abacus, because it destroys the efficiency of Indian arithmetic, which is based on algorithms, which is based on the place value system. He understood the place value system enough to write rad numbers, but he did not understand how it can be used for efficient arithmetic. It took 2 more centuries, 3 more centuries, well, 2 more centuries. So Fibonacci, he understood that you need this for efficient arithmetic. But he does not understand negative numbers. So this is the table of contents from Mahavir's Ganit Sar Sangrah. And as you see, he will talk about positive and negative numbers and so on. And if you see the table from Fibonacci, he does not do that. See, he is talking in chapter 4 on the subtraction of lesser numbers from greater numbers, because this is pebble arithmetic. Subtraction means removing pebbles. You cannot remove more pebbles than are actually there. And this stupid mistake continued to haunt European arithmetic till the 20th century. Because they said, we are superior, our arithmetic must be superior, our pebble arithmetic is the best thing to do, it is the most sensible thing to do. And this persisted. And well, what I want to say is that persisted until the 20th century. I won't give you the whole story, just give a couple of examples. You were mentioning Euler. We were discussing that day. You said, oh, minus infinity is, minus 1 is less than minus infinity. That's not it. You look at his argument. Look at Euler's argument. This is from an original thing. You can translate it, of course, by just using Google Eye. And what he does is, the argument he gives is a very silly argument. He says that minus 1 is less than 0 is less than 1. Take reciprocals. And therefore, minus 1 is greater than infinity. All right. He gives an argument which is a wrong argument. It's not I who am wrong, it is Euler who is wrong. Let's be clear about it. Let's not start with the prejudice that I must be wrong. All right. And then, of course, we know that Euler copied Aryabhat's recursive method, and he was familiar with Indian texts, of course. He wrote an article on the Indian calendar in 1740. And well, we know that Fermat's challenge problem was a solved exercise in Bhaskar and so on, and I will skip that. So, Augustus de Morgan, I want to talk about Augustus de Morgan. He was a dunce, because he wrote these, very influential professor of University College London, who wrote 700 articles. And what did he do? You see, he writes on algebra and calculus, page 11. See what he writes. It's worth seeing. Please, internet, please come on. Okay, so here it is. So you see what he's saying. He's saying that 10 minus 20 is impossible. He's writing this. I'm not writing this. The book is available on archive. We're not talking ancient history. All right. 10 minus 11 plus is not possible. So till the 20th century, this goes on into Hall and Knight textbook, which I studied in my school. Negative numbers possible, not possible in arithmetic, but possible in algebra. And similar thing, study of difficulties in math. So he will do something like that. He will say that, how do you dare say minus 9 is less than 0? How can something be less than nothing? He says it is 10,000 times, see, that is his wording, 10,000 times more possible to believe in the existence of witches and judicial astrology. This is the kind of utter nonsense that he is writing about the study of difficulties with mathematics. Now, if you learn mathematics like that, it is bound to become difficult. That is why it has become difficult. That is why I am saying that the correct way to remedy it is to stop following the West. So that's all. That's the only way to do it. You can't keep.
Stop believing in witches.
Yes. So this is the cartoon that I have made. It deserves a dunce cap for having made such a famous statement. We should not forget that he made such an excessively foolish statement. All right. So now, last point I want to make about De Morgan is that De Morgan got the East India Company to finance. He got this finance, a text publication of a textbook, not a textbook or whatever book you call it, by Yasudas Ramchandra. This is the book. Yasudas means slave of Jesus. Ramchandra, who did this, it was financed by the East India Company under this thing of De Morgan. And what is he saying in this book? Maxima and minima solved by algebra, not by calculus. Why not? Because in calculus you'll say positive, negative, 0, that's the maxima, minima. He doesn't want negative numbers. That's why. So this is what he's doing, and this kind of institutional complicity with serial plagiarists is very common in the West, and it is something which has happened with me several times. So you were talking about Einstein. So this is Michael Atiyah, who serially plagiarized my work. This is his admission by his chamchas in the notices of the American Mathematical Society. There are 2 of my books that he is citing and 1 paper he is citing. And this is an admission, but there is an admission, no apology. Because the idea is you steal 2 times, 3 times, you get caught, then you say, okay, yes, you did it earlier. If you don't get caught, you keep it. No, that's a great way of doing it. So this is in the notices of the American Mathematical Society. The AMS collaborated. It was complicit in it. And my thing was about Einstein's mistake. You can take a look at this. There is this thing, if you like a simple way of looking at it, is a video. All right. So we are not talking about that. Point is there's institutional complicity, and the same thing happened when the University of Exeter, when this theft of calculus, my article on the theft of calculus was itself stolen.
Second order theft.
Second order theft. And then you see they did it, but you see what the kind of cheating they did. Your Vice Chancellor of Exeter University says we didn't call Professor Raju because we sent him a letter and the letter was bounced back. Can you imagine Indian Postal Service sending a letter back to England? So, a complete nonsense. It never was, and they involved a co-plagiarist to sit and as a consultant for it, for the committee, ethics committee. And the same thing again happened, when Manchester University published, it was there in all the pages, and then only 1 newspaper carried a correction on this. If you can read it, I don't know if you can read it. This was there in the front pages of all newspapers in India, 2007. And only HT carried a retraction. All right, and so this is serial plagiarism again and again because they are pretty sure that nobody in India is going to stand up and challenge them. That's the point. Get is from floating point numbers because you are going to use a computer to send a man to the moon. And a computer uses floating point numbers, not real numbers, and floating point numbers don't follow the associative law. So this is the point I made in my Hawaii article. Now these chaps said, well, something to do with floating point numbers. What did they do? They lagaut tukka. They said that floating point numbers, let me show that to you, recent class article, they were used by Kerala mathematicians to derive infinite series. Wonderful. How are you going to use floating point numbers to derive infinite series? This is the statement from the paper on recent class. This is what serial plagiarists do. This is the total lack of understanding, is buffoonery. The worst kind of buffoonery that you can imagine, that is what you find. And it has nothing to do with floating point numbers. Obviously, Kerala mathematicians did not do that because they are recent invention after the digital computer and so on. So let's get back to Newton and Leibniz. So Leibniz, as you know, accused Newton of stealing his discovery and complained to the Royal Society. And all these presidents of the Royal Society seem to be similar, okay, whether it is Atiyah or whether it is Newton. So both will say, of course, that he discovered it independently. And that is the stand today. Both discovered it independently. How was it independent? We have to know. We don't know. But basically what Newton did was that as president of the Royal Society, he appointed a committee to look into the matter. He headed the committee. And he wrote the report exonerating himself. And then he published an anonymous review of it in the proceedings of the Royal Society. So this is the review that he published, and where he talks about many interesting things. The very good thing, you should read it, because although he has a bias, there is no doubt about that, he is still giving solid arguments. So we should look at that. So he published this. So one of the things he says is that Leibniz is the second inventor, because he is thinking of discovery doctrine, Christian discovery doctrine, and therefore he says he is the second inventor, second discoverer. Why should he get the credit? And he says that second inventors have no rights. This is what he says there. He is also to renounce all rights of the differential method of Newton as second inventor, for second inventors have no right. The sole right is there is in the first inventor, and he says it is not even right to divide the credit between him and that other, because that would be an act of injustice. So why should you divide credit between Newton and Madhav or anybody, Taylor, and call it Taylor-Madhav series or whatever? That is an act of injustice according to Newton's own thing. Why should you give even partial credit to Newton for the calculus? That would be an act of injustice according to Newton's own logic, his own standard. All right, so, well, let me go on. But Newton's term for calculus was theory of fluxions. So this was his textbook on calculus, this text, which was posthumously published, method of fluxions and infinite series. And what he says is that, what are these fluxions? Why don't you hear of them today? Where have they vanished? Why doesn't anybody talk about them? Because they were complete nonsense. Fluxions are small particles of flow of time. So what is the flow of time? It's foolish to speak of flow of time. There is this Metrical paradox, which was a copy of Sriharsh. It is described in my first book. You cannot speak of flow of time because that will need a second time in which this time is to flow. You can speak of flow of a river in time. So the conceptual confusion about time was the reason for the failure of Newtonian physics. I have discussed that in my book, and I won't go into it. Obviously, I can't do the whole book in one lecture or explain this. So I will skip the physics and let me go on to our immediate concern. So our immediate concern is that Newton's fluxions are abandoned today as utterly confused. Berkeley criticized Newton's lack of understanding of what he called the theory of fluxions, okay, and they are small particles of flowing time. His point was that howsoever he may have obtained his scientific results, he may have obtained valid scientific results, but if you don't understand how you have obtained those results, then it is not science. That was his point. You must have proper understanding. Without proper understanding, it's not science, because you are quoting, it's like a blind man arriving somewhere without knowing how. So I won't go into all the details of the quote because I don't have so much time. Point I want to make is, yes, certainly Berkeley was a bishop, there is no doubt, and he was hostile because Newton was religiously hostile to the church, extremely hostile. He called these padres as spiritual fornicators, the most evil kinds of men ever to have existed on earth, and so on. And after his death, his papers were never published, they were suppressed. And so I am saying that it wasn't only Berkeley, Karl Marx, who had no religious hostility to Newton, did that. Dedekind, who had no religious hostility, found Newton's things absolutely unacceptable. What is this fluxions he's talking about? So, as he says, this way of introducing differential calculus can make no claims to being scientific. For me, this feeling of dissatisfaction was so overpowering that I made the fixed resolve to find a rigorous foundation for it. So, therefore, today you go with Dedekind cuts or real numbers. You don't use fluxions. So, the point is those real numbers lack infinitesimals. They are an Archimedean ordered field which lacks infinitesimals. Cannot have infinitesimals or infinities. My point is that's a wrong way to understand calculus. That is not the way Indians understood calculus. There's a better way to do it, and the better way involves infinitesimals and infinities, which were there in Brahmagupta. So anyway, this proves two things. It proves that Newton did not understand calculus because it's rejected what he did with fluxions. And it also shows that the practical consequences of Newtonian physics before Dedekind were all obtained without the use of real numbers. So you don't need real numbers for anything practical. The second point I made. So basically, Europeans didn't understand its two aspects of Indian calculus, which was the notion of infinitesimal, and the second was how to sum an infinite series. Because all the mathematicians today, they are brought up on real numbers. I was also teaching. I was also brought up that way. I also taught for so many years. And some of my students are in prominent positions who learned real analysis, are in prominent positions, and they are saying, why have you given up real analysis? We liked your lectures, so what can I do? So there's a big problem in the definition of derivative. First thing is that it does not cover all of physics. So in the real analysis definition, a differentiable function must be continuous. But this does not work for shock waves. So you have situations in physics where your discontinuities may arise because the shock waves, statistical mechanics is done over shock wave is only as thin as a mean free path. And therefore, it represents a discontinuity from the continuum method. So if you accept a discontinuity, then the differential equations of physics will become meaningless and fail. Riemann is one of the persons who made a blunder on this. He thought that the equations of fluid dynamics will be the equations of conservation of mass, momentum, and entropy, whereas entropy increases across a shock. Now you can use a Schwarz derivative where you can differentiate a discontinuous function, but although it defines the derivative of a discontinuous function, Schwarz theory is a linear theory, so you cannot define what is the product of the delta function with the delta function, what is delta into delta. So you can't define that, you can't define compositions and so on. But this is a problem which I did in my PhD thesis, by the way. And similar problem arises in renormalization in quantum field theory. Okay, so it's square of x raised to minus n. So if you have 1 by x, so it is not the same thing as x raised to minus twice n, because it is some principal value and so on. Won't get into technicalities. Point is that it arises central to the renormalization problem of quantum field theory. All the propagators are such Schwarz distributions, if you like, and therefore what I did was that initially I used non-standard analysis in my PhD thesis. Okay, I was a bacha, that is what I understood, and so I used it. And I said this must be the right way to do it, and I applied it to the Schwarz theory. So junction conditions, for example, was in general relativity was one of the papers that I wrote based on that as part of my thesis. I applied non-standard analysis to Schwarz distributions. I said, okay, that seems to be the solution. But then, and that is the major change that I made since then, I'm saying that non-standard analysis is not needed. All that you need is non-Archimedean arithmetic in an ordered field. So non-standard analysis, very complex, extremely complex. I don't think there are, I cannot think of 2 names of Indians who are working on it. So it's extremely complex, and so you need non-Archimedean arithmetic. Now here are my lecture notes on that, which I'm using, which I used earlier in the Mysore course, and it does many things. It will define hyperreal. So this I'm just going through it. I can't, it's not a classroom. So hyperreal numbers, right? So hyperreal numbers are there, and what happens with hyperreal numbers, and what is the polynomial arithmetic with that, and so forth. So I do it as part of the course, and these notes may have some errors because they've all been done very fast. So just the usual stuff of quotient field and so on, nothing very thing, but polynomials over a field. So they obey non-Archimedean arithmetic, because you define, how do you define order among polynomials and so on. So all that is there. This is, for example, you have these hyperreal numbers and so forth. I will skip this. It is there online if you want to look at it. All right. So this is just division of polynomials and so on. And okay.
It's like a completely European kind of mathematics.
Yes.
You're doing.
I'm doing.
I mean, some kind of agreematic thing and all that.
Yes. So why should no. 1 minute. 1 minute. My point is, you have to address the Purva Paksh. To address the Purva Paksh, you have to address the Purva Paksh. You have to do it like this. So I'm not doing it this way. I'm just saying that even axiomatically it can be done. That's not what I'm doing. That's what can be done in current axiomatic mathematics. Okay, so this title is Axiomatic Infinitesimals. So I have to teach the Purva Paksh that within axiomatics also you can have infinitesimals. All right, that's the idea. And I think it's you have to address it, and this is basically Avyakt Ganit of Bhaskar. It's a very simple idea that if you are saying something, how can I say that x is less than n? It may be anything. I must know the value of x. And this is part of Avyakt Ganit, and it's part of Bij Ganit, and I also do that. So the point is that if you have infinitesimals, then you can sum the infinite geometric series as Nilkant did, and this is described here. It's also described that you need something more. You need that a new philosophy of mathematics, which is zeroism, which is different from that of axiomatic math. So here's the article on zeroism. So you can take a look at it if you want. So it describes how this sort of thing can be done. You are discarding infinitesimals and so on. So there's nothing Western here, but the axiomatic thing has to be done for them to understand the Purva Paksh, that hyperreal numbers are not good enough. So this is better than using hyperreal numbers, which makes calculus easy after making the beginning impossibly complicated. So that is what it is. Now I want to go to the last thing, which is myths and superstitions. I want to go in a little bit quickly. That Dedekind cuts, what did he do? Dedekind's cut was that if you cut a line anywhere, then you must get a number there, not a gap. That is his idea. So why is that idea coming up? Because there are no axiomatic proofs in the book, Euclid book. Now we are talking about the book which is in front of us. There are no axiomatic proofs there, not even in its first proposition. So what is the first proposition? Oh God. Okay, so this is the challenge that I raised. 2 lakh challenge prize to give evidence of Pythagoras, connection between Pythagoras and the theorem attributed to him, and any axiomatic proof of it before Hilbert 1899. Hilbert was the first person who gives actual axiomatic proofs. There are no axiomatic proofs in the book by Euclid. It's a religious book. It's a book on Egyptian mystery geometry. I can't go into all that, but that is what Plato did. So there is a religious superstition there, and I'm also saying that this religious superstition was taken over by the crusading dogma of reason. So axiomatic proof was first used not in mathematics but in theology by Aquinas. So this is, so you don't have, well, first proposition of Euclid is here, it's a fish figure. So the idea is that you are given a line segment and you are asked to construct an equilateral triangle on it. So you take, you keep a compass box, keep a compass, measure this and draw one arc like that. Keep it in the other place, again measure this, draw an arc like that, and then join it. Now this has a mystical significance. I'm not going to go into that what is this cross and so on and so forth, and what is the fish and why the fish is important. It is there in my book, Euclid and Jesus. I don't go into this. But the point is, how do you know these two actually intersect? Empirically, I can see they are intersecting. How do I know axiomatically that they are intersecting? So they are not intersecting, and therefore Dedekind's idea was to provide a system of axiomatic numbers by means of which you could say that they are actually intersecting axiomatically. And in Hilbert's synthetic geometry, of course, you do it. So I teach this to children. That see, you are talking about invisible points and so on, and how do you locate anything, and there's a Euclid challenge prize, and there are these different types of geometries that we are never told about: Hilbert synthetic geometry, Birkhoff's metric geometry, then the compass box geometry, and then how do they compare with Euclidean geometry, so-called Euclidean geometry, and whether they are compatible with each other or not. So this is my Raju Ganit thing, which is then meant for schools. I will skip that. So the point is, there is no Euclid either. And I have offered a challenge prize for it long ago, 2011. There's a presentation you can look at, or you can look at the book. I'll just show you the book. If the transparency, it comes up. So Euclid was a black woman. I said this made the people in South Africa very agitated against me. They abused me and abused me. So how dare you say he was a black woman and he was a white man? So that was their idea. And the point I'm making is here in the subtitle: how and why the church changed mathematics and Christianity across two religious wars. So this is the point that is being made. And so now I have to unfortunately tell these kids whom I am teaching that why does mathematics need to be taught with so many lies? Start with a lie about Euclid and say he did something superior and it's not there in the book, and then you say Newton and he did calculus and so on. Why do you need to teach? Why are lies so essential to the teaching of mathematics? So they have no answer. I have second point I am making is that you have myths like this which are taught because obviously it was a system used by the church. And for the church, myth and superstition are the means of power. So the superstition that you are taught is that this axiomatic proof is superior. This is there in the 9th standard text. That, oh, you know, Egyptians and Babylonians and so on, they had some Pythagorean proposition, but they did it for practical use. What is the impractical use that you want? They had reason, but that's a complete lie. So saying that there's a difference, let's understand the critical difference between axiomatic mathematics and Ganit. That Ganit accepts pratyaksh praman. How do you know that? That's there in the nice sutra. It is there as part of all Indian thought. So it's very simple: pratyaksh, anuman, upman, and shabda. Those are the means of proof, and you can accept some of them or reject some of them. As Buddhists will accept something, Lokayats will reject something, and so on. But everything revolves around that. Now, nobody rejects the empirical, but axiomatic mathematics rejects the empirical. So here is the definition of mathematical proof. So it's a sequence of statements in which each statement is either an axiom or is a direct consequence of some of the preceding statements. The theorem is the last sentence of an axiom. Wait, I have not finished. Hang on. It goes a little longer than that. So basically you are using a rule of reasoning such as A implies B, A therefore B, and you are not allowing the empirical. So this is stated in the class 9 text. So each statement must be established using only logic. Beware of being deceived by what you see. So what you see is fallible. This is being taught to children. What you see is fallible. Don't believe it. What you can infer is not fallible. Now that is wrong. How do you say it is not fallible? Inference, I mean, I ask my students how many times you get bad marks in exam because you made a mistake. How do you say that proofs are not fallible? So of course they are fallible. And how many big mathematicians made errors in proofs? So just by that authority you can't get it right. And so this is how many times. Simple example is game of chess. Purely deductive game. Every human being loses to a machine. You will lose to my phone now. Every human being will lose to my phone most of the time. Why? Because you always make a mistake. The machine does not make a mistake. If you are asked to do a complex deductive task, you are bound to make mistakes. And the greatest mathematicians, I just mentioned Riemann, made a mistake. So if math is being done for science and technology, which is why we do it, why should we reject the empirical? Why should that make math better or superior? Rejecting the empirical. Science needs the empirical, technology needs the empirical. Why do you want to reject it? And how do you say it makes it superior? So this is the superstition on the basis of which we are teaching, and which everybody is doing this, and it works better for theology. Because there is the angel theorem that Aquinas had. So many angels can fit on the head of a pin. And now there are people who will tell you that this is not true, and therefore I have a quotation from Summa Theologica, direct from Summa Theologica. You can go to it if the internet works. So angels in relation, okay, whether several angels can be in the same time, the same place. This is from the Summa Theologica. I am doing it on the internet and not putting in any substitution here. So please look at it. So, so this was used by the crusading theology of reason, which was invented to counter the Akli Kalam that Muslims had. And the point is that any nonsense proposition whatsoever, I repeat, like my rabbit theorem, any nonsense proposition whatsoever can be proved, provided you give me the authority to lay down the axioms. And the only person who has the authority to lay down the axioms of mathematics today are the Westerners. So, claiming that it is infallible, it's a foolish superstition. It is not true that deductive reasoning is infallible, and more foolish than this, and it hurts the nation. Okay, so I think this time I've really finished. Now you can clap. All right. Questions?
I think we can perhaps take questions later, but maybe we could move straight to the next paper, which is by Professor Eva Orthman, who's Professor of Iranian Studies at the University of Göttingen. And she was also served at Professor of Islamic Studies in Bonn, where she was the director of the Institute of Oriental and Asian Studies. And since 2018, she's the director of the Institute of Iranian Studies at the University of Göttingen. Her special interest is in subjects relating to the Mughal Empire, history of science, astral sciences, mathematics, occult sciences, and the Indo-Persian transfer of knowledge and culture. She will be speaking on the translation of mathematical and astral sciences into Persian.
Good afternoon, and on the top of all, I'm a European. And I will today not speak about Europeans, but I will speak about a translation gone from Indian languages into Persian. And I want to begin by thanking very much for this very honorable invitation, which I was very happy to get, and I'm very pleased to be here. And it's a great opportunity for historians of science, and so I'm especially happy that I was invited to talk about translation in the field of astral sciences and mathematics. And maybe I should add, as Professor Najaf Haidar and Chandrasekhar had done, I am not trained in astronomy and mathematics, but I'm more coming from the sociocultural background, still looking at what happens when texts are translated, how is transmission done, which ways of transferring knowledge from one language into another language were taken, and this has also changed over time. It depends very much from the people involved. So, translation and the use of linguae francae, or common languages, are at the heart of scientific exchange across different cultures. For the exchange between the subcontinent and the Islamic world, 3 languages were crucial. For India, Sanskrit, which has dominated literary production in South Asia, at least from the 4th century on. In many cases, we, however, do not know if it was direct translations from Sanskrit or via some intermediate Indic languages. For the Islamic world, first Arabic, and we have heard about that, and then Persian, which acquired the status of common language for the eastern part of the Islamic world from the 11th century on. The emergence of Arabic and Persian as languages of science and culture went along with the thirst of knowledge. In Baghdad, as we have already heard today, hundreds of texts were translated into Arabic in the context of the so-called translation movement. The term is less used today. For Persian, the exchange with the Sanskritic world became crucial. The astral sciences were in both cases among the first sciences to be translated. This does not come as a surprise. Astronomy and astrology have often played a crucial part in translation movements. Looking at translations from Sanskrit, different stages can be discerned, and we have heard about some of this already today. The first period with translations from Sanskrit into Arabic in the Abbasid period. Then the Ghaznavid period with the eminent scholar Al-Biruni, again with Arabic and Sanskrit. Later, from the period of Firuz Shah Tughlaq on up to colonial times, we have translations from Sanskrit into Persian, but also vice versa from Persian into Sanskrit. These stages are what we are going to look in my talk, with an emphasis on 3 specific translated texts, and we have heard about some of them already, so we see these are crucial texts. The Brat Samhita, the Nujum al-Ulum, and the Siddhanta Sindhu. I will be brief about the Abbasid period.
What is the second text?
I will talk about in detail. Why is the Abbasid period important? Because in the Arabic and Islamic world, in that period, the foundation of science has been laid. Much has been taken over from Greek and the Hellenistic heritage, but this was not the only source of knowledge. We also have many translations from Syriac, Middle Persian, and Sanskrit. Unfortunately, the translations from Sanskrit have to a large degree not been preserved, but we know about them from other texts. Not all Sanskrit lore was directly taken over from Sanskrit texts. Some information also came via Middle Persian. We know that Indian astronomical knowledge had already been taken over in the Sasanian Empire, and Professor Schecker has pointed to that, and had influenced the production of astronomical tables there. These texts were then translated into Arabic and used in astronomy. The 2 traditions which merged in Abbasid Baghdad, Greek and Sanskrit, often transmitted via Middle Persian, were however not totally different, since Indian astronomy had been influenced by Greek astronomy since the 2nd century CE. This made it easy to integrate Indian elements into the Ptolemaic system. Besides Indian astronomy, mathematics were also transmitted, especially, and we have heard a lot about that, so I will be very brief, the numerical system. We have heard that Al-Khwarizmi and his treatise on Indian numerals was of outstanding importance for the transmission of the decimal system to the West. What we have not been talking about is that in Arabic astrosciences, the decimal system was hardly used. All astronomical tables were written in the so-called abjad system, the alphanumerical system based on the attribution of numbers to the letters of the alphabet. With Al-Biruni, and we have heard about him, who traveled to India in the 11th century, the exchange becomes more palpable. Trained as an astronomer, he was especially eager to understand the Indian astronomical and astrological systems. About half of his Kitab Malil Hind, his book on India, and we heard about it, is devoted to these 2 fields of knowledge, which are heavily intertwined. His information is quite relevant for the study of the development of the astrosciences in India, since its translation preserves materials otherwise lost. To give you an idea about his perception of astronomy in India, I will quote from his book. The science of stars is most famous among them because the matters of religion are dependent on it. The title of astrologer and astronomer does not occur by mere computation to those who do not understand the judgments of the stars. That which our authors know as Sindhind is their Siddhanta. This name refers to each science of computation of stars that rises to the highest rank for them, even though, for us, they fell short of our sieges. And I think 3 points are relevant here. First, Al-Biruni sees a direct link between the interest in the astrosciences and religion. Second, and this has not been mentioned here, he considers astrology to be of outstanding importance in India, so important that it was not enough to know astronomical calculations to be counted as an expert in astronomy or astrosciences, and here it becomes difficult to translate. Third, he appreciated the astronomical tables and calculations, but thought that those produced in the Islamic world were exacter in his time. This most probably had to do with the extensive observations done in the Islamic world and with the high standards of observational tools there, among them the very efficient astrolabe. Astrolabes, first produced in antiquity, were developed into a kind of multifunctional mini-computers in the Arabic world. The science of astrolabe making was highly appreciated, and astrolabes were very often beautifully executed and could be pieces of art. Many treatises were written on how to use it, and you see here an outstanding example of an astrolabe produced by the so-called Lahori family. According to his own words, Al-Biruni translated a treatise on the astrolabe into Sanskrit, testifying to the interest in this instrument from the side of Sanskrit scholars. They called it the Yantra Raja, the king of instruments. Al-Biruni's translation has not been preserved. The first preserved Sanskrit translation dates back to the period of Firoz Shah Tughlaq, and the oldest surviving astrolabes in Sanskrit is from 1605 from Gujarat. With the Delhi Sultanate period, we enter into the long centuries of translations from Sanskrit and other Indian languages into Persian, and to a certain extent, vice versa also. To start with, let's have a look at an overview of translated texts. In the frame of the Perso-Indica project, which is dedicated to providing an analytical survey of Persian works on Indian learned traditions, we have prepared a list of Persian texts which have been translated or which are suspect of having been influenced by Indic learning. Since we did not yet see all these texts and did not yet study them, much of the information is based on the existing manuscript catalogs. They might need correction in the future because, as many of you know, the titles in catalogs might be misguiding, so you get different titles for two books, or for a book which turns out to be the same in the end. So this has to be studied thoroughly in the future. On this list, we find 3 different translations of Bhaskara's Bijaganita, his treatise on algebra, 3 translations of Bhaskara's Lilavati, a treatise on geometry and arithmetic, 3 translations of his Karanakutuhara dedicated to Jyotisha. We furthermore have 2 translations of the Brat Samhita and 1 revision of a translation, a text of which I will talk in a moment. The Ratanmala Danujum on astral sciences also was translated 3 times. And that's one of the questions we have in the project. How do these different translations differ from each other, and where was there a need to translate and retranslate the same text so often? You can ask me these questions, but I have some answers, but not final answers for that at the moment. There are about 20 more texts on astronomy and mathematics which probably are translations or have been inspired by Indian knowledge, and 20 more which might have been influenced by Indian texts. So all this has to be checked on the copies. In addition to that, we have 8 Zijas which might have been influenced by Indian astronomy, and there are at least 5 Sanskrit translations. And yeah, there are at least 5 Sanskrit translations of Persian astronomical works. In addition to what has been mentioned so far, we also have to consider encyclopedic treatises which include chapters on mathematics, astronomy, and astrology. One important text in this regard is the Nujum al-Ulum, the stars of the sciences, so it has already the stars in the title, an encyclopedia produced in Bijapur during the Adil Shahi period. And this is the second text about which I'm going to talk just in a few moments. We can thus note that the number of translated texts is quite high, and that translations were done in both directions. However, the number of translations into Persian was certainly much higher than vice versa. Let's now have a closer look at 3 specific cases. The first is the Brat Samhita. the Tarjume Kitabe Varahi in Persian. And we have heard about the Brat Samhita. So I will focus more or less on the translation. So we have heard that the text has originally been prepared in the 6th century by Varahamihira. The first translation into Persian was done for Firuz Shah Tughlaq by Abdulaziz Shamsi Sari, and several copies of the text have been preserved, and one is on the display and exhibition. The Brat Samhita deals with all kinds of prognostic sciences, like astrology, but also augury, physiognomy, and many other techniques. The first chapters are dedicated to the astral sciences. One important section is about the course of the planets and the lunar nodes, Rahu and Ketu, on comets and on the conjunctions of the moon with the planets. The transits of sun and moon and eclipses are also dealt with. The translation generally is very close to the Sanskrit original. 8 chapters of the book have, however, not been translated, since the translator or his patron, so the man who was giving the money, the king, did not consider these chapters to be appropriate for translation. They are about religion and ritual. Especially in the sections on astronomy, we understand that the translator himself obviously was a specialist in astronomy and astrology, since he does not always translate verbatim, but changes some of the content to adapt it to contemporary astronomical knowledge. As an example, let's take the solar and lunar eclipses. In the Sanskrit version, the mythological aspects of Rahu and Ketu, the head and the tail of the dragon, are discussed at length. The shape of the dragon, its movements, etc. are described. However, Varahamihira also points to inconsistencies in the system, gives a scientific explanation of eclipses, and admonishes the reader to calculate eclipses through the moon's parallax, and not to believe in portents, omens, etc. for the determination. The Persian version is much briefer and simply says, Ras, the dragon's head, is in the shape of a snake to which Brahma has given the power to cause solar and lunar eclipses. In conjunction with the sun, it covers it with its mouth, and in opposition to the moon, it covers it with its tail. Instead of referring to parallaxes, the text then states that Ras and Zanab are always at 180 degrees from each other, and that the lunar nodes move 3 degrees 11 minutes per day. This is a clear deviation from the original text, which is most probably due to the scientific background of the translator. And if anybody has a better explanation, I'm very happy to listen to it.
Just some one point. I think Brat Samhita does not talk of Ketu as a node. It's comet in Brat Samhita.
Sorry?
Several Ketus mentioned in Brat Samhita. They're all comets. Only Rahu is mentioned.
Is only Rahu mentioned? I would check it. Yeah, thank you. I will recheck it. Another interesting case of deference is the description of the astrologer. The Sanskrit version gives rather detailed information about his appearance and behavior, explaining that virtues and faults often depend on good and bad physical characteristics. We can compare this description with descriptions in medical texts about the requirements of a physician. Much less information about the required appearance is given in the Persian version, which adds instead that an astrologer should abstain from alcohol and fornication. Interestingly, that is really interesting, the foundational texts an astrologer should be familiar with are the same in both versions, so no recent texts have been added by the translator. 2 more notes on the translational techniques. The Persian version keeps most of the Sanskrit terminology. This means that the technical terms are transliterated and explained when mentioned for the first time. And I can show it to you here. So we have here the beginning of the chapter, Babe bisto yekom, dar bayane, and then comes the Sanskrit term, Meg Garb Lakshaman, and my apologies for my extremely poor pronunciation of Sanskrit terms. And then comes the Persian explanation, that's to say, at which time a cloud becomes, and the Persian term is abistan, which means something like pregnant or fructiferous, so filled with water in that case. And so throughout the rest of the book, and the book is quite long, the transliterated terms are used, making it very challenging to follow the argument for somebody unfamiliar with Sanskrit terminology. The translator was well aware, however, of difficulties a Persian reader might encounter when reading the text. He therefore adds many explanations of technical terms, measurements, etc., like, for example, explaining the calendar system of India and how to calculate months. Taken together, I assume that in this case, the translation was done not by a team, but by a single person, and that this single person knew Sanskrit. Otherwise, I cannot imagine how he should have kept so much Sanskrit terminology throughout this very long text. So, let's now turn to the second example, the Nujum al-Ulum, my favorite text right at the moment. The Nujum al-Ulum is an encyclopedic text which has been translated at the Adil Shahi court, probably by Ali Adil Shah himself or by a member of his court. The book was supposed to consist of 53 chapters, so we have a table of content at the beginning. But only 6 chapters have so far been discovered, and one may doubt if the book has ever been finished. However, even these 6 chapters are very long. The Chester Beatty manuscript, which is the most beautiful copy of the text, consists of 348 folios and includes about 400 paintings. And maybe also, since we are talking here about manuscripts, the manuscript is available digitally on the webpage of the Chester Beatty, and you can enlarge every image, you can download them. It's really, I would say, a very, very good example of how to provide digital copies of a text. It's wonderful.
What would be the original Sanskrit name for this?
I don't think, let me say it so, that it's not the translation of a single text. It's a text which has been written in new, and it has been compiled from different sources. And I will show you a little bit of the compilation techniques, but what we can do is identify sources for single parts of the book, at least for the 6 chapters we have. And it's such a pity, I'm just saying it. If you read the titles of the other chapters, you just think, please, let me find these chapters. But I'm already very happy with the 6 chapters. And
What does the title mean?
huh? Yes, they are at the Chester Beatty. There are at least 2 more incomplete copies of the text, but the Chester Beatty is the manuscript I have used so far, and you can download them, and it's really a pleasure, just a visual pleasure. I just put here an image which is totally unrelated to what I'm saying about, just to give you an idea about the brilliant colors and the beauty of the manuscript. And if you just type Chester Beatty, Nujum al-Ulum, you get it. I can also send a link. So, now, the first 2 chapters in our book are dedicated to the heavens, the signs of the zodiac, the planets, their place of rising, the exact positions, and this according to the calendars of India and Khorasan. And they are followed in chapter 3 by extended sections on astrological charts. Unfortunately, and I have to say that, and that's a challenge also, the chapters are in disorder, and probably some folios are also missing. That makes it very difficult to say how many pages are related to each chapter. So that's still ongoing work for me also. So in the following, I want, as I said, to demonstrate how the text carefully combines and mixes different scientific traditions. Let's therefore have at first a look at the description and the depiction of the astral constellations and the planets. These depictions, at first glance, look entirely Islamic. They are based on Ptolemy and the constellations described in the Almagest, a book translated into Arabic in the 8th and 9th century. So it has been translated at least twice. In the 10th century, these constellations have been depicted by Abdurrahman as-Sufi in his famous Kitab Suwar al-Kawakib. This Arabic origin of the zodiacal sign and their depictions are again and again referred to in the Nujum, and indeed they look very similar. And I give you here on the right side, you see the depiction in the Suwar al-Kawakib by as-Sufi. On the left side, you see the depiction in the Nujum al-Ulum. There are slight differences. The most important difference is that in the Suwar al-Kawakib, you get each image twice. Once are seen from below, from Earth, and once are seen from up, as if you were outside the entire celestial system and looking from upstairs down. So let's say the perspective of God, if you want. And so this is not reproduced. The Nujum al-Ulum always gives only one perspective. So this similarity is, however, only true for the signs situated not on the zodiac. The zodiacal signs are different because in the depiction of the zodiacal signs, Sanskrit astral knowledge is integrated. So for every zodiacal sign, we get first the description as in the Suwar al-Kawakib. And that's the first image you see here. You see here Leo, and in the text it is referring to the Arab tradition and how the stars are situated on the body of Leo. Then there is a description to which nakshatras, the zodiacal sign, is identified. So it says this zodiacal sign of Leo consists of Magha, Purva, and the first third of Uttara. Then comes, and this is something I would be very happy if anybody can give me a clue where it comes from, the depiction of the nakshatras. And I will have to look into that in more detail, from which let's say iconographic tradition the depiction of the nakshatras here is exactly coming. And after that, so after this, let's say, Sanskrit part, it goes back to the images related to every single degree of the zodiac. So in total, 360 images are related to the degrees of the zodiac, 30 to each burj, to each zodiacal sign. And that's the first three depictions related to Leo. And they have very well been described in the Sirr al-Maktoum by Fakhr ad-Din Arazi. So we are here back in another Arabic tradition, which is, however, not exactly a Ptolemaic tradition. So, in the description of the planets, again, Arabic and Persian and Indian traditions are mixed. As an example, let's have a look at the sun. And every single of these depictions are so beautiful. So we see the sun here accompanied by two lions. The combination of sun and lion is very typical for the Arabo-Persian tradition. Also, usually it's only one lion, not two. All the other elements, however, rather have an Indian background. The sun is seated on a chariot. It has 4 arms and it holds a club and a flower in its hand. According to the text which is accompanying the image, the sun has a father and a mother, 2 wives and many children, and is related to the fire and the Kshatriyas. This association of specific attributes with the planets can be found in India from the mid-2nd century CE on. At that time, planets started to be associated with specific colors, metals, and perfumes, and also riding animals, and were furthermore related to gods. The origins of Graha Puja can be found here. The description of the planets and their iconography also had a deep impact on astral magic in the Arab world in Europe. The worship of the planets in Haran in the 8th and 9th century has clearly been influenced by Indian practices, and from there, these notions spread to Europe. We thus find similar attributes in Arabic and Sanskrit texts. However, the parental affiliation And many of the details in this specific depiction do not belong to the canon of attributes we find in standard Arabic and Persian texts. So they come here from some Indian background, and they testify, therefore, to the combination of different traditions in the Nujum al-Ulum. Let's now turn to the astronomical parts of the book. From the point of history of astronomy, this is a very interesting section which needs much more research. So I'm just touching upon this topic. So the text has turned out to be a translation of the Varshika Tantra by Devanāgarī. Varshika Tantra means annual system, because the calculations were valid for 1 year only, and they had to be renewed every year. In Persian, the book is called Kitab-i Varshik. The original text must have been written at the latest in the 16th century, maybe already in the 14th. That's what David Pingree assumes. It is from South India, and the Varshika Tantra seems to have been popular in Karnataka. Devanāgarī probably was of Dravidian origin. That's at least what Pingree assesses. The Sanskrit version of the Varshika Tantra has not yet been edited, but there are some copies, at least 5 or 6, I think. Recently, 2 commentaries on this text in Sanskrit and Kannada have been discovered and used to reconstruct the original text, and an edition of the first chapter has been provided. These commentaries date from the 17th century. It is not clear when the Persian translation has been done, and if it was prepared for the Nujum al-Ulum, or if it has been taken from an already existing text. I rather assume that the translation had been done separately, and that the person who wrote the Nujum al-Ulum took this book, this translation, and placed it into the book. But I'm not so sure. There is some dating which refers to the translation. So if it has been done separately, it is very close to the compilation of the book. So I will give you a very short comparison of the Persian version based on with the Sanskrit version. So the Persian version consists of 10 chapters. It is in total 83 folios, and since the pages are rather large and there are no illustrations in the astronomy, there's absolutely no, not a single illustration, which is quite astonishing in a book full of illustration. That's also one reason for which I take it probably was an independent text. So it's a quite long text. The text starts with a glossary, giving short, often very short explanations of Sanskrit terminology. As an example, let's take Shaka. That's where I have here the arrow, and it says Yani Matta Tarikh, the beginning of an epoch or an era.
What is the distinction between the rose and the black color?
The red is the Sanskrit term and the black is the Persian.
Oh, just.
Yeah. So it is a way of organizing the text, so you can.
Word by word they put it.
Yeah, but that's only the first page, and after the first page you have to know, and then the text is full of Sanskrit terminology. In this regard, it comes quite close to the Varamihira translation. Here also, I cannot think about translator who did not know Sanskrit, because I have to go back to the first page for more or less every single line to understand what it could be. So it really is, it's challenging to look at that text. Devanāgarī seems not to have been a very modest person, and I would like to have his self-confidence. He translates the texts by beginning with the following: I, the author of this precious book, Varshik, by the name of Devanāgarī, whose position among the astronomers, the educated people, and the scholars is like the position of the sun among the stars with regard to greatness and light. I like that. And so he was obviously very self-confident if this is according to the Sanskrit version. And I would like to counter-check this because in the commentary, it starts totally differently. So this has to be checked in the future. So the first chapter is dedicated to the extrapolation of the positions of the planets by mathematical operations. The book starts by explaining how to convert Shaka years into Kali years, so years elapsed since the beginning of the Kali Yuga. The text furthermore suggests an easy way to calculate the length of the year as 52 weeks, that's 364 days, plus 1007 divided by 800 days. And the ratio behind this is that if you count the year in weeks, every 800 years you have to add 1007 days to get the correct number of years and days. In the Persian version, this calculation is explained in some detail, and it becomes clear that it's used to determine for any given moment the weekday and the exact time of the day in Gahri, Pala, etc. The Persian version is not, the Sanskrit version obviously gives then the mathematical explanations for all these calculations. Unfortunately, this is missing in the Persian version, and however, it could be somewhere else in the later section. So since the text has been somehow disturbed, it could come at a later moment, and I am searching for that because I think it has been added somewhere else.
Sorry, this particular text, Varshika Tantra, you have said Kannada and Sanskrit commentary subject.
Yeah.
Now it has been published, Kannada translation, translated into English, Kannada commentary.
The entire text?
Yeah, it's called Ganita Gannadi.
Ah, okay.
And exactly, 1007 by 800, all those things are there.
I will be very happy because I only found the publication or the edition of the first chapter with an English translation, and they were announcing that they want to have the full. So I didn't see yet the full. I will be very happy.
Our friend has done it, one lady.
I will be very happy to learn the exact bibliographical data of that. Yeah.
And it is mostly based on Surya Siddhanta. That's what I found,
Okay. Yeah, maybe we can talk about that later. And as I said, to understand the exact discrepancies between the Persian text and the Sanskrit text, of course, it would better be not to look at the commentary, but to look at the original Sanskrit text, which I think, but maybe you know better, has not yet been edited. So the last information I had was that it's not edited and not translated. So there is much work left to be done. So a little bit, I try to hurry up because I just very briefly wanted to look at a third text, which is related to translation from Persian into Sanskrit, because we also have this direction. And this genre of text is generally known as Tajika texts. So these are translations from Persian into Sanskrit. Tajik going back to Tazi, which is a word for Arabic. So at least 5 texts are known, and the interest was especially in the Zij tradition. That's, as you know, and we have talked about it a lot, astronomical books with many tables. So sometimes between the 9th and the 13th century, the traditional astral sciences in India started to change under the influence of Arabic and Persian texts. One of the most influential features introduced into astrology were the so-called Tajika yogas, describing aspects of planets and the effect of the strength or weakness of a planet. These aspects have been taken over from the Arab astronomer Sahal ibn Bishr from the 9th century, probably not directly from his text, but through some translations or copies and excerpts. In the field of astronomy, the so-called Zijes were of specific interest to astronomers, and I show you here one Zij from tables of Asicsi, as far as I remember. The total number of sieges produced in Arabic and Persian is very high. But not all sieges, as you certainly all know, are based on observations. One can also produce a new siege by calculations. That's one of the reasons for which the siege Ulugh Bey, which was produced in Samarkand in the 15th century, was especially popular. It was based on new observations. It was the first siege, to the best of my knowledge, to be translated into Sanskrit. This translation was done in the period of Akbar, but it was followed by further translations like the Siege Shah Jahani. The text I will refer to was also already mentioned today. Therefore I will be very brief. It is the Siddhanta Sithandu by Nityananda. The text, and I'm referring here to the study by Anuj Mishra, who has worked extensively on the Sanskrit and the Persian version of this text. He was, as we have heard this morning, a Hindu astronomer working at the court of Shah Jahan, and his translation is based on a Siege Shah Jahani, which was produced by Mullah Farid. We have already heard about the two books, so I skip that. So the Siddhanta Sithandu was finished in 1630 in prose and verse, and we also have heard that there is at least one copy, and I think even more than one copy, in Jaipur in the Palace Library. As Anuj Mishra has shown, in the Siddhanta Sindhu, the translation does not only reproduce in Sanskrit what is written in Persian, but tries to communicate. While the readers of a Persian siege were supposed to be familiar with the general terminology and the structure of a siege, Nityananda did not suppose the Sanskrit readers to understand the terminology, and he also does not use much transliteration. So in this regard, he is really different from the first two examples I gave you. And so he creates some new Sanskrit term, and he adds definitions and explanations. And what I find is interesting is that he also adapted the text to his audience. And the example Anuj Mishra gives is the chapter on finding a direction, because in the Persian version, the example always taken is how to find the direction of Mecca. This was needed for ritual prayer. But in the Sanskrit translation, it's not the direction of Mecca, but the direction of Kashi, which is explained. So it's also a sacred locality, but a different one, and of more importance for the intended readership. Taking one of the chapter headings as an example, we see how the Sanskrit version differs from the Persian text. For example, instead of lines, the Sanskrit text writes cells. The Sanskrit heading furthermore refers to the Trairasika, we have heard about that, to the rule of three. And we have heard about this morning, which is so important in the Indian science of calculation. And the text also refers to the Yavanas and their way of calculation, something which is not in the Persian way. The Siddhanta Sindhu is thus an interesting example for how Persian knowledge was transferred into Sanskrit and which adaptation processes were deemed necessary in doing so. To sum up, in the field of astrosciences, the exchange of ideas has always been of major importance. The fact that Indian astronomy had been largely influenced by Greek ideas facilitated the exchange with Arabic and Persian astronomy, which had been based to a large extent on Greek texts, especially on Ptolemy. From the Delhi period, the Sultanate period on, many translations from Sanskrit to Persian were produced, with the astrosciences and mathematics as one major field of interest. And if you are more interested in it, you can look at the Perso Indica website, where we have an index showing the different fields in which translations were done, and they are also done in the field of medicine, in the field of veterinary medicine, in the field of philosophy, etc., etc. So it's a large topic of which the astrosciences are only a small segment. Translations were done up to the colonial period, not only at the Mughal court, but also at many other places, for example, at in the Deccan Sultanates like the Nujum al-Mulum. The selection of texts, the choice of terminology, the adaptation to own concepts, the amount of additional information given, all this dependent from the qualification of the translator, the patron's preferences, and the expected audience or readership. These texts thus allow us to explore interaction between different scientific communities in India, which is a major goal of the Perso-Indica project. The study of such texts is often difficult due to the limitations of researchers, and I have to include myself and my many limitations. So it's not so easy to find a specialist who knows Persian and Sanskrit and astronomy, so to really fully grasp the different interests at play, and so cooperation is very much needed. So there is indeed a huge need for cooperation, and I very much hope that such cooperation will become more widespread in the future, and maybe this conference is a good starting point for that. So thank you. And
we won't have I think maybe not a discussion right now, because we're also a bit short for time, and we have 2 more speakers and the valedictory. So maybe should we go straight into the next speaker? Yeah, Professor Alva.
Yeah, we'll go to the next 2 presentations, and I request Professor Alvar and also Professor Deepak Parmashivan to, if possible, make it slightly briefer, because I think the valediction